Okay, so we have the exercise 3. System responses as signal spectrum. The first exercise is similar to the last time, where you just analyze the system and determine what is the system coefficients A and B, stem plotting the first values of impulse response, and from that picture you can determine if that is the FIR or IIR, and then plot the frequency response. Oops, don't want to do that. Plot the frequency response, and then insert a figure of amplitude and phase response, and is it linear or non-linear phase response, again from the graph. If it's a straight line, then it's linear, the phase response. If something else, a curve, then it's non-linear phase response. The fourth part, zeros and poles of the system. And then from the zero pole plot, you can actually determine at which frequency the system has highest attenuation, or actually calculating the locations of the zeros. You can pinpoint exactly what is the place where the system attenuates the signal the most. You just need to find the complex angle and transfer that into the linear the real frequency axis. Then plotting group delay. Group delay, well, as some other, also there might be some differences on the names on MATLAB and Octa, but MATLAB has much better the help system. So the documentation of function is much better. Scale the system such that it has unity gain as at passband, which is a good property for filter. You generally you don't want to have the filter which has anything else than unity gain. Since then you can have separate gain blocks to multiply the signal. So that will be volume control. Then the seventh, sound sample chirp with some noise, again similar to last time, and then spectrum of it and spectrogram, and applying your system to filter the data and to see what it looks like on a picture. Good. All right, let's take a look at Octave. Where's my Octave here? Yeah, the Octave doesn't, it's not that snappy to start. No, it feels like it's not starting at all. Let's start it again. Okay, yeah. Didn't start at the beginning. Okay, good. Mm -hmm. Okay, this command window is a little bit messed up, but maybe I can deal with that. A bit messed up. There we go. So first, for the exercise 3, let's not use that system. I will show you, since you already know how to do that one. Let's take another system from scratch and design it by eyeballing the zeros and poles just to prove a point. So let's first set up the system that we have sampling rate equals, say, 2000 hertz. So this would be, camera on. There we go. So a system sampling rate 2000 hertz, and we design the system so that it has 0 points minimal in here. So that is then 750 hertz. And then we have the system gain. Okay, we could also add 1 here. So we have also third the 0, so it's third degree system, at least from the zeros, and then just put some poles, 1 pole here at distance 0.2, and then maybe at 250 hertz, pole pair, and all of these distances to unit circle. Well, the radius from origo would be 0.8. This is our system, zeros and poles. Example, okay, let's see. System responses. And example from graph. We have the sampling rate is 2000 hertz. Then we have the zeros at the following angles. Omega. Omegas are, the real axis 0 is easy. It is at point -1, right? Location, -1. Okay, remember the roots have the column vector. Then this, if it's a system coefficient, then it's a row vector. So that's why I'm using the line separator here, semicolon. And then we have exponential of pi, 2 times pi times 750 divided by 2000. Ooh, doesn't show up because of my Windows setting. It shows up on the command history though. But I don't see it here. That ain't good. I will restart the system. Restart this one if I get any better. Interesting. Crashed. Okay. There we go. System responses example from graph. Fs equals 2000 hertz, and Then the zeros. Angles of zeros are omega z equals, okay, let's make it this way. So omega's actually not -1, but it's pi. Then we have pi times 750 divided by 2000 and pi or minus pi times 750 divided by 2000 and not pi but 2 pi. So that was just a way to translate the the real frequency information into complex plane. Wait a minute. Semicolon, not that kind of thing. Okay, there we go. Those are the complex angles, and then my zeros are simply exp j times omega z. And then corresponding poles. I will start with omega. The angles of poles will be, first one is 0, then we have 250 and minus 250. Okay. And my poles would be 0.8 times exponential of j times omega p. Okay. That kind of complex angles and numbers. And now we can plot them, zeros and poles, on a figure. Okay, looks quite the same as in my video graph here. I can close that one then. So my system design is something like this, and how to calculate the, when now these are the roots, the corresponding system coefficients. So BB are the polynomial defined by these roots. Whoops, how come it actually, okay, calculation inaccuracy. Real part of that one. Yeah, this should be real numbers. It gave me something, probably machine epsilon times I. And A equals polynomial defined by poles. Let's see, do I need to do the same? Okay, this is real numbers in it on the first place. So for some reason, I had to just take the real part of the zeros because otherwise it would have this very tiny amount of complexity in it. I don't like complex things. Yeah, I almost say a really politically non-correct joke here, but let's not go into that. Okay, so A's and B's are there. Now we can actually calculate, for example, the frequency response, or what shall we actually do here on the exercise? Stem plot the first 12 values of the impulse response. Okay, when you have these coefficients, actually what you can do then is you may take the point of interest here, for example, from this region of interest, and then calculate the impulse response. So delta equals to there. This is the impulse function. And then we can calculate the impulse response. HH equals filter BB AA DD. Filter is the realization of the system. So this is impulse response. There is also, I think it's called impz, a function that calculates the impulse response, and I think it also plots it. So it's up to you which one to use, but let me put this one in a new figure, stem NNHH. So the impulse response plot looks like that. Interesting, very interesting. Okay, it's this FIR or IIR. It's easy to check. We have a maximum of 4 coefficients, which means the maximum delay is 3. Then we can actually calculate, for example, like this, sum of HH values when NN is greater than 3. If this is non-zero, wait a minute. Well, it might actually work that way. So we are calculating the values of sum of sorry. Sum doesn't say anything, actually the absolute sum. This one will show if there are any non-zero values after that point, and okay, plenty. That is non-zero. It means that you have a IIR system. There are, so you can eyeball it from the figure, but actually this is a way you can actually do it without plotting a figure. For example, on a automated system, which is set checking if the system is FIR or IIR. Non-zero values after on impulse. Response after third and the highest order delay. It's IIR system from the graph. But on the other hand, you can see already on the Z-plane. I plotted the zeros and poles because that was my, well, I started on those zeros and poles. I just wanted to see if that is matching my beautiful picture. Okay, so now we have the impulse response calculated. What was the next step? Okay. Frequency response. Simply frequency response is called FRECH, where you have the parameters are the system coefficients BB and AA, then how many points you want to calculate it. I like powers of 2. It's up to you how many points you use, and then the sampling rate. You can always plot help FRECH to see how you actually can call it. By the way, on MATLAB, it's more complex than that. It has more parameters and more ways of calling it. But anyways, so pretty nice low pass filter, although I couldn't quite match the flat gain, so I have a little bit too much gain here. So maybe my pole, I could probably tweak either this pole a little bit further from the unit circle or these two poles closer. So let's tweak. Just to get a better flat response. So poles. I tweaked the first one since the pole. Okay, escape. Oh. The poles here. So if I move this one further, so first pole would be 0.7. Let's see what this one does for the system. AA, poly BB. Frequency response. Figure frequency response. Not quite yet there. Tweak it a little bit more. As you can see, there must be better ways to do it, since this would take ages to fit this by hand. Fortunately, there's a comprehensive package of filter design tools on MATLAB. Poles. Okay. AA, poly PB, and then again figure. Ha! Better. Now I have quite flat passband response. See. Okay, and compared to our 3-point running average filter, do I have it somewhere easily? So frequency response. There I have one picture of this is the 4-point running average. Look at the stop band attenuation, only about 12 dB. 12 dB. And here we have, well, first of all, this is unity gain, but we have, let's see, 20, 40, about 60 decibels of stop band attenuation. Just by very simple third order system. Okay, looks pretty cool. So frequency response like that. Is it linear or non-linear? Well, on passband, this is not straight line. This is not straight line anywhere. So definitely a non-linear phase response. And what is more important is a group delay. I think it was called GRP delay, BBAA. Group delay, how to use it. Okay, yeah, the same way as on Flex C. So new figure, group delay, BBAA, how many data points, observation points, and sampling rate. Okay. When I talk about nonlinear phase response, this is now the time time delay of the signal in some samples, I think so, but we have 2 kilohertz signal, the sampling rate, so each time step is 0.5 milliseconds. So practically we have about 1 millisecond to 1.5 millisecond. Oh, actually, let's see, that's 2 milliseconds. Oh, yeah, 2.5 millisecond, in between 1 and 2.5 millisecond time delay in the passband. So group delay done like that. Oh, by the way, oops, yeah, I should have probably put the semicolon. This normally doesn't happen in MATLAB, since if there is no output given, then the MATLAB doesn't, plot those. But anyways, but we have the command history still here. Let me do one small thing here. Just in case, save my command history this far. And by the way, I should have also recalculated the impulse response. So it does change a bit. This is a better view of the impulse response. And of course, the Z-plane. So this is the real system, not the one that I plotted first. I tweaked it. Okay, so we started from this picture. Well, actually, we started from here, plotted the amplitude response. I wasn't so satisfied with it, so I moved move that one pole closer to the center, which basically flattened the passband. And well, I could also calculate the impulse response, and this is still IIR system. It doesn't change it at all. So after the third, the delayed impulse response value, you still have non-zero components. So it's still a IIR system, and with let's see, group delay of that one. Argus diagram done, group delay. Then only thing to do is to scale the system such that it has unity gain at passband. Okay. Scaling for unity gain is simply, I'll do it this is the brute force engineering approach, which usually works as well as any. It might actually have 0.01 dB difference to the what it's supposed to be, but still it's the same in my point of view. So we can actually calculate the complex, the frequency response. We just give the output value for Fritz, BB, AA, 1024. Doesn't matter if it's actually a Doesn't matter, the frequency scale doesn't matter here. That's a complex, supposed to be the complex. Yeah, it is complex, the table. So, okay, those are the frequency response values. What we can do then, find what is the maximum the amplitude. Maximum absolute value of HC. That's the absolute, maximum gain. And we can actually rescale the for unity gain well, we just implement a one gain block before the system, which reverses the system gain. So this is the scaling of the BB coefs. And after that, frequency response. Looks a little bit funny here because it actually goes to minus infinity here, but let's zoom it a little bit. Okay. Oh, that ain't bad. That ain't actually bad at all for a low pass filter. So it has the minus 3 dB point somewhere in here, about 230 hertz or so, or 250 or no, actually it's a little closer to 260 maybe. So 260 hertz or so. Well, we can take a closer look. Okay, minus 3 dB. So it's, yeah. So it's about 270 hertz, maybe. 270 hertz, and then it has almost 60 decibels of stop band attenuation, although the transition bandwidth is quite wide. There. So now it has been transferred into unity gain filter, low pass filter, which we can use. All right. Then we should have some sort of sound sample. Generate a sound sample which consists of a chirp signal. There I should actually show you how to generate the chirp by say without that already written function. Okay, now yes, that's actually quite pedagogical, since what is frequency? That is my question. If you have a function f of t is sinusoid of 2 times pi times g t. So we have a generating function gt. For constant frequency, we have g of t equals just that f times t. That's the, well, it's linear by time. How about if we want to have the frequency, for example, starts at 0 and reaches fs over 2 at, say, 1 second. Meaning, well, if it was chirp, let me do it first with a chirp. Chirp, chirp, chirp. T vector at time, frequency at time 0, time t1, and then frequency at time t1, vector of time. So, for example, if we have vector of times equals from 0 to 1 over fs to 1 second there, and f0 is 0 and t1 is 1 second and f1 is 1000 hertz. Haha, yes, this will be great. Then we do a spectrogram first and then go back to the go down to the individual spectrum. So chirp 1, let's call this chirp true. Chirp tt f0 t1 f1, and it looks like yeah, the plotting tool has some problem here, or actually it's not. It's just that you get aliasing effects here. So we started from low frequencies. Low frequencies, and then it ended up having this very high frequency here at the end. So we have the at Nyquist rate at the end. There we go. So that's our signal. And let's make the spectrogram. Now careful. Horizontal axis. I put it already here. And okay, on MATLAB, I think the spectrogram is now called spectrogram. On Octave, there's old name specgram, and also another function called spectrogram, but on MATLAB it's called spectrogram. Or, well, search for the documentation which gives you the spectrogram. But be careful because that spectrogram is written by mathematicians and they don't care about the axis, which way they go. But here is the old-fashioned spectrogram. Right, and here we have how to use it. X, N, Fs, and window. So data, how many data points, sampling rate, window width. So what size window we are using there, and then how many, how much is the overlap, and then we might actually also want to set the direction of the plot. We might actually need to use that argument too, but we'll see. So specgram data chirp true, and then we have number of n is number of points in the segment length is, I for example start with 256. What's the second next one? The fs sampling rate. Yes. Sampling rate. Then next parameter. Sorry about that. Okay, what is the window size? So actually we can go either smaller or actually bigger window size, meaning artificially better resolution, but 256 is just fine. And then number overlap pins, half of that one. But I think those are the defaults. So spectrum, that one should do it. Where did it go? There. Ha. Chirp. Okay. Basically, I could actually go to smaller size. 128. The spectral resolution. Then you get better time resolution, and spectral resolution is already, say, good enough. What are the good parameters? Well, it totally depends on your data and how it looks like. This is a graphical representation of signal. It means that when it looks nice, it is okay. There is no good or bad unless it looks ugly. So this is one of the rare occasions that engineers need to actually judge if a graph looks ugly or not. So this is anyways a signal representation in frequency domain. So we have the time going horizontally and frequency going vertically. Now be careful when you are using the MATLAB. There's a spectrogram which gives you time on the vertical axis, which is totally, it's not wrong, but it's awkward. Nowhere else in any culture you have time 0 at the lower left corner growing up. I would understand it if it was a water flow where you have the 0 time is on the top left corner and the time kind of flows down like that, meaning the same way as you read text, you start from the top line and go lower, but not the way the MATLAB has the default on it. So you need to take a look at the MATLAB. Let's see, do I get the documentation of MATLAB spectrogram. Okay, you need to actually add there. Was it that one? There. Yes. The form which has the frequency lock specifies the axis on which to plot the frequencies. Otherwise, these kind of pictures where you have, well, this looks okay. Have they fixed the yeah, this is wrong. This is totally wrong. So frequency, okay, frequency rising kind of makes sense in border diagrams, frequencies on the horizontal axis, but think of a time axis here. Isn't that actually awkward? So time goes from 0 to the forward, growing from bottom to top. Does not make any sense. So what you need to do, make sure that you have yeah, spectrogram so that you plot it on the frequency on y-axis. So that y-axis is important on your exercise. Otherwise, I will give you bad time. I will give you bad time about awkward plots. Okay, but anyways, so this is correct. On Octave, it looks like the frequency axis is the normal axis. Excellent. So that's when you have only engineers and physicists working on the tool, unlike the MathWorks has been now contaminated by too many theoretical mathematicians. Although they are also needed to help engineers. Okay, so yeah, so that's chirp what I generated from using the chirp function. Okay, let's think of the how about the obvious. So we have signal, I call it chirp false. Would be sinusoid of 2 times pi times f, which is now starts from 0 and basically at 1 second it's 1000, so 0 to 1000 it's a linear. Oh, sorry. So the frequency is actually directly proportional to the time. So this is my frequency, 1000 times t. At 1 second, that gives 1000, right? Oops. That's my frequency. And then just ft. So this is 2 pi ft. What is wrong with that? I'll show you. Let's calculate the spectrogram. What went wrong? Okay, I give you a hint. What is the frequency of 2 pi ft? It's basically frequency of 2 times pi times f times t equals simply dft divided by dt equals that constant frequency f. How about frequency of 2 times pi times, well, I will leave that one just out, 1000 times t times t equals 2. Oh, 1000 times 2 times t. So that 2 factor of 2, as we can see here, we have double of the rate as here. Actually comes from the fact that when you are doing the when you're calculating the frequency of any sinusoid, you take the derivative of the time-related component here. That is the frequency. In this case, we got the you get the derivative of t squared with this 2 times t. So we can fix that by dividing this whole thing by 2. And fix. Yeah, looks the same. So so practically, when you do that kind of sinusoid of 2 times pi times g of t, then and you have this you want where the gt generates function g something else gg then that generating polynomial generating function here is simply integral of gt over t. So that actually works also for the constant. If your GGT is only the constant f, then the integral of constant over time t is simply f times t. Da. So practically, this is how you would do the generating any shape, the frequency on the for say this kind of sinusoidal functions. Okay, I hope that was entertaining. You might actually need it sometime, or if you don't have the chirp for some reason already written, you now remember how to write your own chirp that doesn't do the double rate, or just add the engineering factor of 0.5 here there. But anyways, so now we have actually the spectrogram. I warned you about the axis there. Use this kind of presentation, so you have time on horizontal axis and the frequency on vertical axis. Spectrogram done. We can actually now, I will show you the last part, filtering the sample. What happens? Simple thing. We have that system BBAA. So we have the I'll call it SS equals filter BBAA and data. I use my CH fix new figure. So filter actually provided this kind of picture. So where did we have this? We have 750 hertz was one of those lines. Maybe there is some more attenuation. Let me yeah, that's not good. I will do it over again. 108. So tweaking some parameters to get the picture which looks better. Oh, this one doesn't look any better. There. Okay. Now I have a little bit more frequency resolution. So at 750, there should be some attenuation also there. Well, it doesn't really show up well on this picture. Maybe I can see when if I know that what the system, the amplitude response looks like, then I can actually guess that okay, maybe at that point we would have some attenuation there on the signal. I would need some smaller time step, I think. Yeah, this actually looks a little bit better. So now we have at time step around here 0.75 seconds, which is where our signal was 750 hertz. There is attenuation on amplitude. Okay, maybe it works. Maybe it works as required, but on the other hand, your signal will be easier to interpret since it has that noise. Okay, maybe if I add some noise. Ah, yes, added some noise and I can see it easier. There's a chirp, and then there's the filter, actually filters the noise, especially the noise at 750 hertz and then at the Nyquist rate. And it's a low pass filter. Good, good, good. Close some of those. And then how about the individual spectrum of a subsample? First, how to take subsamples. We have a signal called, well, for example, that CH fix. If I want to have a subsample, I'm called subsample. I can take actually any region here. I, for example, take first indexes to 250 data points and start it anywhere between 0 to the size of that CH fix minus the length. So for example, I can start it at the middle. We have 1000 data points. I can start it. Yeah. Oh, actually I had 2000 data points. Yes. I can basically take a look at what is the individual spectrum at around the middle. About the middle. Well, that would be, whoops. 1000 is middle, but then I will shift it left a bit. Okay, there I have my subsample at the middle. So let me plot that subsample there. Okay, looks like that. And it went to the frequency response plot. That's fine. I don't use it anymore. But anyways, there's the signal. It's still frequency is changing, and now we do the spectrum analysis for that one. And we start by making the FFT. So fast Fourier transformation. When you have 2 to power something, then you can use the FFT algorithm. Otherwise, if you have some other number of samples, then the MATLAB automatically uses the discrete Fourier transformation. You don't see the difference in short data samples. But fast Fourier transformation is the way to go. So that's the Fourier transformation. So power spectrum, I will say PS equals F subs dot times complex conjugate of F subs. That's the definition. So that is power spectrum. The corresponding frequency axis would be starts from 0, ends to 255 divided by 256 times sampling rate. So it's a linear the transformation bit. So basically, we have the sampling rate is the base on the fundamental highest rate on the data. So it has the negative frequencies there too. That's why it has not just for the Nyquist rate. Okay, and Fourier transformation is just transforming those data points, in this case 256 of them, into spectral space and fulfills from 0 to 2 pi. So this is then the linear physical frequencies axis information would be just like that. So those frequencies. And we need only half of them, since the spectrum is supposed to be symmetrical. Okay, so we take only from first one to 128 plus 1, since the first index is for 0 frequency, and then that n divided by 2 plus 1 is the Nyquist rate. So this is from indexes from 0 to Fs over 2, including the Fs over 2. And now we can actually plot. Not yet. Power spectrum, never linear. Decibels, 10 times log of 10 of PS. Power in dB, of course. And now we can plot. Plot FF inch, that's the frequency axis, the first half of it, and then dB, PS, inch. That's the power in dB. Oops. Of course. Ah, looks like a hat again. Or is this, almost a sign of ah, hey, this is Batman, right? Those are the pointy ears. Yeah, it's Batman cape. Oh, right. Or it's a freak this power spectrum of my signal which has no noise on it. So this is a poor signal which doesn't have any noise. So what we can hear is the envelope of the window. That cape of that Batman is actually the actually that window. Okay, so and we at that we have frequencies between chirp frequencies from between 450 to 550 hertz. Kind of sort of makes sense. So at the middle we should have 500 hertz, but on the other hand we took points on both sides. Yeah, so this actually makes a lot of sense. Ha. So that's how you pick a location. So what I'm looking at here right now is a spectrum somewhere around this point here. Scale line. 0.5, 0.5, and y is 0 and 1000. Okay, right there, that line. Oh, it probably doesn't show up at all, but well, I did my best. There. Okay, now it shows up. So I calculate the this individual spectrum at that time point. Okay, good. So I have covered plenty of stuff today. So started with the defining system zeros and poles. Let me close the window so I can go through the stuff. So first, again, first the zeros and poles. Okay, of the system. That's a modified already. Then basically plotted the impulse response, calculated the impulse response somewhere. Here, that's the impulse response of the system. That's IIR system, a amplitude response and or the phase response, showing that this is non-linear phase response. And this is for the unity gain system. Already unity gain. Calculate the group delay, basically from the phase response. Using the, so what I'm using here, it's just the same. Sorry about that again. Yeah, it doesn't show up. I'm using exactly the same system coefficients A and B here all the time. And then what else? I basically calculated chirp. Chirp, and showed you how not to do the chirp or any other functional form of the sinusoid. And then individual individual spectrum of that one. From that frequency. A little bit wider region though. Okay, so I think that covers more or less everything. So actually in here, when I say filter sound sample with the system Q1, actually, I would say Q6, which is the unity gain at passband system. That make it looks the same, but this one makes just a little bit more sense. So you have scaled the filter to unity gain, and then you use it. Okay, so that is my part for today. So next, what I will be doing, I will be saving everything and start producing those video files. And right now I will